one of several thousand particle physicists in the world who are involved in the Large Hadron Collider, or LHC project at CERN. I'm on the LHCb experiment because I want to understand CP violation. I want to know where this difference between matter and antimatter comes from and why the universe looks the way it does. We think at the beginning of the universe, in the Big Bang, we had equal amounts of matter and antimatter being created. And yet, if we look at the universe around us today, we don't have equal amounts of matter and antimatter, we just have matter. And we know this because if matter and antimatter meet, they annihilate, they explode and release loads and loads of energy. And this quite clearly doesn't happen around us. You know, I don't cause explosions by sitting on the chair. I don't see explosions when air meets a building. We're all the same type of matter here. Now, in order to go from a universe which consists of half antimatter and half matter to a universe that consists all of matter, then something really big and fundamental must have happened. And one condition for this to have happened is for an effect called CP violation to come into play. Now, CP violation is nothing more than a difference in the behaviour of matter and antimatter. And quite clearly, if we have half matter and antimatter to start with, and we now have matter today, they must behave differently in order to reach that state. We don't really understand this effect, but we want to understand it in particle physics because it is the reason why we're here today in the universe. It is the reason why the universe looks as it does to us. It's a very important unanswered question in physics and particle physics and astrophysics all over the place. We've built the LHCb experiment to answer this question, and we've done this because LHCb is specifically designed to study the properties of particles containing B quarks. These particles are great microscopes onto CP violation because the effects of matter and antimatter in particles containing a B quark is different. Matter B quarks and antimatter B quarks behave slightly differently, and they behave more differently than other types of particles. So it's a great thing to look at to try and understand this. This is our nerve centre of where we build detectors, and in fact this room that you can see here on the right is one of our cleanest clean rooms. It's actually one of the cleanest places in the world. It's what we call a class 100 clean room, which means that it must contain less than 100 particles of dust per cubic metre of air. And we need to have this level of cleanliness when we build our detectors to stop contamination.
This is what we're building at Liverpool. Inside the blue box is a module, and we've 42 of these modules that will eventually form the heart of the LHCb experiment at CERN. The module itself is composed of 3 components. The base at the bottom, a bit in the middle, which is black, which is enormously stiff and yet enormously light carbon fibre, and then at the top, the most complicated part, you'll see that in green, which actually holds the electronics, which is capable of reading out the silicon sensor, which is in silver at the top. The silicon sensor has about 2,000 strips, each one of which can detect the passage of an ionizing particle with a precision of better than a few microns at almost 40 million times per second. On the other side of the module, you'll see that there's also electronics and also another piece of silicon. One piece of silicon records the distance from the beam that the particle went through, and the other piece of silicon on the other side records how far round the beam azimuthally the particle went through, allowing us to completely reconstruct the position of the particle in 3 dimensions.
I wire bond the wires to make the connections from the 128 channel amplifying chip down to the sensor. These are very small 25 micron aluminium wire, which is about a quarter of a diameter of the hair on your head. And it comes down, and the force and the pressure resonates the wedge, and it's this resonation causes the friction that fuses the 2 materials together, and it welds the wire to the amplifying chip and then across to the sensor. And so we can have a readout when a particle travels through the sensor, it reads out onto the chip. So it's nice to be part of something, to build something and know I've contributed.
It's such a seductive idea to me to be able to look deep into the heart of matter, pick it apart like pass the parcel or an onion skin, just to see what it's made of. And the fact that in particle physics we think that everything is made of a few fundamental constituents, a very few ingredients which make everything in the universe, not just us or what's on the Earth, but things that are happening on the other side of the galaxy and other galaxies, I think is an absolutely wonderful idea.